Good morning, all. Write your seat number and name in the chat box. Yesterday, we learned about the anomalous behavior of oxygen and fluorine. So this is very important question for the board examination regarding, because in this chapter, periodic trends, anomalous behavior, structures, and reactions. This is asked for the board examination. As the topic is very big, remember the most important points. Anomalous behavior, always it is asked for 2 marks or 3 marks. No any question of 1 mark will be asked on it. So yesterday we discussed about the anomalous behavior of oxygen. Anomalous means why oxygen shows exceptional behavior than the other elements in the respective groups. Because of the small size, high electronegativity and absence of d orbital, this oxygen shows exceptional behavior. And we already discussed this exceptional behavior. Physical state, oxygen is a gas. Then other elements are solid at room temperature. Oxygen is diatomic. It always exists as O2 molecule, and other elements can exist as a polyatomic molecules. Magnetic, regarding the magnetic property, oxygen is a paramagnetic, and while other elements are diamagnetic. Oxidation state, oxygen generally shows -2 oxidation state. And in case of peroxide, it shows -1 oxidation state. But +2 oxidation state, it is found in only one compound, that is OF2, remember. So these are the oxidation states of oxygen, and the other elements in the respective group can show -2, +2, +4, +6, because the higher oxidation states are possible because they are having the d orbital, remember. So as the d orbital is there and oxygen do not having d orbital, so the higher oxidation states can be possible if excitation of electron takes place from lower energy level to higher energy level. Then the nature of hydrides, you know, the famous hydride of oxygen is water. Water is a liquid at room temperature, and other hydrides of the elements are gaseous. These are also very bad smell and poisonous gases at room temperature. So this is also the exceptional behavior. Then hydrogen, only the oxygen having the capacity to form hydrogen bonds because it is more electronegative, and other elements do not form hydrogen bonds, remember. So this is explained yesterday. Also, I discussed this anomalous behavior of fluorine. Again and again, I am reminding you, this is very, very important for the board examination and all the examinations conducted in the entire year. On this topic, the question will be there. Explain the exceptional behavior or anomalous behavior, or why fluorine behaves exceptionally than the other elements. So the question can be reshuffled, but the answer is same. This is also explained yesterday why the fluorine shows exceptional behavior. The reasons are same because of the small size, highest electronegativity, low fluorine-fluorine bond dissociation energy, and a non-availability of d orbitals because fluorine do not having the d orbitals. And these are the points of difference. Number one is the reactivity. Fluorine is the most reactive because the atomic size is very less, and the bond dissociation energy is also very low. Then hydrogen bonding, fluorine can show hydrogen bonding because the electronegativity is very high. Other elements do not form the hydrogen bonds. Then next point is behavior of HF. HF, you know, this is a hydrofluoric acid. This bond is very strong bond. Hydrogen and fluorine bond is very strong. So this hydrogen cannot be removed easily. So HF is a weak acid, remember. HF is a weak acid. HF is a liquid at room temperature, while the other halogen acids are gases. And HI is a very strong acid because iodine and the hydrogen bond is very weak, so hydrogen can be removed easily. Again, we will discuss these properties of this HF, HCl, HBr, HI in the hydrides of group 17. Oxidation state also we discussed yesterday. Fluorine always shows -1 oxidation state in all its compounds, remember. So this can be asked for the board examination for 1 mark. Other elements of this group can show +3. -1 is a compulsory for these halogens. Other than the -1 oxidation state, other chlorine, bromine, iodine can show these oxidation state. +1. +1 means 1 electron can be given, 3 electrons can be given, +5 means 5 electrons can be given, and +7 means 7 electrons can be given. This is higher oxidation states are possible, this +3, +5, +7, because they are having the d orbital. As d orbital is there, so the excitation of electron takes place. So remember this. Fluorine always shows -1, and other elements can show these oxidation state. Then electron gain enthalpy values. Electron gain enthalpy values of fluorine and chlorine both are negative, but electron gain enthalpy value of fluorine is less negative than the chlorine because of the small size. Remember, this trend is again repeated in oxygen also. Oxygen having less negative electron gain enthalpy values than the sulfur because of the small size. Then the nature of compounds being highly electronegative, fluorine having tendency to form ionic compounds. Ionic compounds, and what is the covalent compounds? In 11th standard also we studied. So in case of ionic compounds, the electron is transferred, and in covalent compounds there is a sharing of electrons. So other elements in the respective groups, they forms the covalent compounds, but fluorine always having tendency to form ionic compounds. Then last part of difference is polyhalide ions. Fluorine does not form polyhalide ions because the reason is absence of d orbital. As fluorine do not having the d orbital, fluorine does not form polyhalide ions, and other elements of these groups can form the polyhalide ions because they are having the presence of d orbital, and this fluorine do not having the d orbital. So this is explained yesterday, and this is a quick revision. Again, today we will start the new part, that is chemical properties. Chemical properties of group 16, 17, and 18. In these chemical properties, first one is oxidation state. So one by one we will discuss the oxidation state of group 16, then group 17, and then group 18. As already I discussed the oxidation state of this oxygen, sulfur. Oxygen, before the oxidation state, you must know the outermost electronic configuration is NH2NP4. This is a general electronic configuration of group 16, remember. Means these oxygen family requires only 2 electrons because there are 4 electrons in this p orbital. After gaining the 2 electrons, this will be stable. So this oxygen family can attain the inert gas configuration by gaining the 2 electrons. So forming E2 minus ions. E2 means by gaining 2 electrons or by sharing 2 electrons, forming 2 covalent bonds, they can achieve the stable electronic configuration. So this oxygen generally shows -2 oxidation state. -2 oxidation state indicates by gaining 2 electrons, by accepting 2 electrons, this will be stable. So -2, this is a general oxidation state of oxygen, and +2 oxidation state is possible in, I am talking about the oxygen only. +2 oxidation state is possible in only one case, that is OF2. So below it is discussed oxygen being highly electronegative. Highly electronegative means it is having tendency to accept electrons, remember. So it shows common oxidation state is -2. Generally, oxygen shows oxidation state -2, except 2 cases. First one is OF2. In case of OF2, as fluorine shows -1 oxidation state, so oxygen will show the +2 oxidation state. This is the only compound on the earth in which oxygen having the +2 oxidation state. And in case of peroxides, remember, So peroxides are H2O2, this is hydrogen peroxide, and sodium peroxide. In case of these peroxides, oxygen shows -1 oxidation state. So these rules of oxidation state also we studied in 11th standard also. Oxygen generally shows oxidation state -2, but in case of peroxide, it shows oxidation state -1. And only in this OF2 compound, it is having the oxidation state +2. So this is for the oxygen, and for the other elements can show +2. Here +2 means 2 electrons can be given, 4 electrons can be given, 6 electrons can be given. So the other elements than the oxygen, sulfur, then selenium, then tellurium, then polonium can show these oxidation state +2, +4, +6 oxidation state, and +4 and +6 oxidation states are more common. These higher oxidation states are possible because of presence of d orbital, remember, and oxygen do not having the d orbital. So this stability of +6 oxidation state decreases from top to bottom, remember. Means this stability of +6 oxidation state decreases, and the stability of +4 oxidation state increases from top to bottom due to this inert pair effect. Then the bonding is always covalent, remember. The bonding in +6 oxidation state and +4 oxidation state is always covalent, not ionic. So this may be asked for 1 mark only. No any bigger question will be asked on the oxidation state. So oxidation state of group 16 elements, it is completed. Then I am coming to the oxidation state of group 17. Group 17, these are the halogens. So this is the general electronic configuration. NH2, NP5, this is the general electronic configuration of halogens. The halogens required, see the electronic configuration carefully, NH2 and NP5 here. So after gaining 1 electron, they will attain the stable electronic configuration. It is equal to the noble gas. So by gaining 1 electron, E minus ions. E minus means when electron is gained, they form E minus ions, or by sharing 1 electron, forming 1 covalent bond. So generally, they having the -1 oxidation state. -1 means after gaining 1 electron, they will attain the stable electronic configuration. So all the halogens shows -1 oxidation state, remember. Fluorine, already we learned about the fluorine. Fluorine always shows -1 oxidation state. But addition to this -1 oxidation state, the chlorine, bromine, iron, iodine can show +1. Means 1 electron can be given, 3 electrons can be given, 5 electrons can be given, 7 electrons can be given. This is possible only in case of chlorine, bromine, and iodine, because they having the d orbital, remember. Fluorine do not having the d orbital, so fluorine do not shows higher oxidation state. Chlorine always shows -1, but this chlorine, bromine, and iodine, in addition to -1, they can show +1, +3, +5, +7 oxidation state. And this is due to the presence of d orbital, remember. Because in case of chlorine, bromine, and iodine, a d orbital is there. In a chlorine, in fluorine, d orbital is not there. So expanded octet is not possible there. But in addition to this oxidation state, +4 and +6 oxidation states are possible in oxides and oxoacids of chlorine and bromine. In next part, we will see these oxoacids of chlorine and bromine. We will discuss in the next part. So remember, in addition to these oxidation state, also +4 and +6 oxidation states are also there in oxoacids of chlorine and bromine. And fluorine is electronegative, so this is -1 is repeated again and again. So on this topic, oxidation, explain the oxidation state of group 17 elements. This question can be asked for 1 mark or 2 mark. So we have to write the oxidation states and general electronic configuration. Fluorine shows which oxidation state, chlorine shows which oxidation state, and in oxoacids only, chlorine and bromine shows +4 and +6. Then I am coming to the group 18 elements. Group 18 elements are noble gases. As the word indicates, noble means these do not disturb to anyone, because their electronic configuration is stable. NS2 NP6, we can see here, this is a general electronic configuration of group 18 elements. As the p orbital is having 6 electron, it is completely filled. Also the capacity of s orbital is only 2 electron, it is also completely filled. So they do not having tendency to gain or lose electrons, they are stable. So these are called as zero valent. Zero valent means the valence is zero, and when the valence is zero, they do not use electrons, do not accept electrons. So always they exist in monoatomic gases. But nowadays, some compounds of these noble gases are found with respect to xenon. So as the xenon is atomic size of xenon, it is very large. If we see the zero group elements, first one is helium, second one is neon, helium, neon, then argon, then krypton, and then xenon. So xenon is quite one, two, three, four, fourth or fifth position. So as it is down the group, atomic size is increases because electron is added in the new shell. So xenon having some tendency to form some compounds. In case of xenon, paired electrons can be promoted to the empty d orbital, because xenon is having the d orbital, empty d orbital. So if the excitation takes place there, excitation takes place always when the energy is accepted. So the excitation means the electrons, pair electrons can be shifted in the empty d orbital. So if the unpaired electrons are there, fluorine, the xenon can form the compounds with this fluorine and oxygen. Some compounds are shown here, XEF2. So here in always fluorine is having -1 oxidation state. So this xenon having the +2 oxidation state. Then in case of XeF4, fluorine having -1. So 4 into -1, it will be -4. So xenon will show +4 oxidation state. In XeF6, this is xenon hexafluoride, +6, it is oxidation state shown by this xenon. Now I am coming to XeO3. Oxygen is having -2, 3 into -2, it is -6. So xenon is shown +6 oxidation state. Now again I am coming to XeOF4. Here oxygen is -2, fluorine is -1. So -4 plus this -2, it becomes -6. So -6, and the xenon will show +6 oxidation state. So these are the some compounds formed by the xenon, remember. So these are the some noble gases. Now this word is not used because they can form the compounds. Xenon compounds are possible. These xenon compounds also we will discuss in the last part of this chapter. Some xenon compounds are also given. So remember, 1 mark question will be asked on it. Write the different oxidation states, or explain the oxidation state of these noble gases. So oxidation state, this property is completed. Oxidation state we discussed of group 16 elements, that is oxygen family. Then group 17 halogen family, and group 18, this is noble gases. Then the next part is, next property is reactivity towards hydrogen. When all these elements of group 16, group 17, and group 16 and group 17 elements can react with hydrogen to form hydrides, remember. So hydrides of group 16 elements we will discuss first. Hydrides means when these elements react with hydrogen, they form hydrides. Which type of hydrides? H2E type of, where E is these elements: oxygen, sulfur, selenium, tellurium, and polonium. And the famous hydride is water. This is water is a hydride of oxygen. H2S, this is hydride of sulfur. H2Se, this is a hydride of selenium. H2Te, this is a hydride of tellurium. And H2PO, this is a hydride of polonium. So the group 16 element shows these types of hydrides, remember. H2O, H2S. Only this is a liquid at room temperature, and the H2S, H2Se, H2T, H2PO, all these are poisonous and very bad smelling gases. Uh, so it is discussed here, the properties of hydrides. H2O is colorless, odorless liquid, while the H2S, H2AC, H2T, these are the hydrides of other elements. These are colorless, bad smelling. Remember, it is very having the very bad smell. H2S in 11th standard also we know this smell of H2S. It is used for the detection of acidic radical and basic radical from the salt. It is very bad odor. Rotten eggs like smell of this H2S. It is very poisonous gas. If it is inhaled in more quantity, the person can die. So these are the some properties of hydrides. All hydrides having the angular structure. H2O also, you know, the structure is angular. The oxygen having sp3 hybridization. This sulfur is also having sp3 hybridization. This selenium is also having the sp3 hybridization during this hydride. So sp3 hybridization is common for the central atom. Oxygen is central here, sulfur is central, selenium is central, tellurium is central. As the structure of water is there, oxygen is as central and two hydrogens are V-shaped structure is there. So all these hydrides having the angular structure with sp3 hybridization of the central atom. And the main properties of these hydrides are weakly acidic, remember. Weakly acidic water is not acidic, not basic, it is a neutral, but these H2S, H2AC, these are weakly acidic in nature. The stability, the thermal stability decreases from H2O to H2PO. H2O is more stable. And the stability depends upon the bond dissociation energy. We can see this table. So with respect to this table, we can see this is a melting point, boiling point. I'm not interested in melting point. I'm interested in this bond dissociation energy. See, bond dissociation energy of this H and E means oxygen and this hydrogen requires 463 kilojoules per mole. This energy is required. So this H2O is thermally more stable. And see the bond dissociation energy of H2T, 238. So this bond can be easily removed, the bond between tellurium and hydrogen. So this is more acidic. Acidic means if this hydrogen is easily removed, it is called as more acidic. And this is also thermally less stable. Water is thermally more stable. And this can act as a reducing agent. This cannot act as a reducing agent. So these properties are given here due to decrease in bond dissociation energy of He down the group. All the hydrides except H2O, but this is the reducing property. Reducing property means if the hydrogen is easily given, it acts as a reducing agent. So we discussed the hydrides of group 16 elements. Now I am coming to the hydrides of group 17 elements. So remember one thing on this topic, hydrides of group 17 elements, always one question is asked for board exam. Which is more acidic and which is less acidic, which is thermally more stable. So I will explain the trick how to remember which is more acidic and which is less acidic. You know, these halogens always exist as in diatomic. So X2, where X is fluorine, chlorine, bromine, and iodine. When these halogens reacts with hydrogen, they form twice HX. Twice HX means twice HCl. When they reacts with fluorine, they forms twice HF, then twice HCl, then twice HBr, then twice HI. So these are the hydrofluoric acid, then hydrochloric acid, hydrobromic acid, and hydroiodic acid. All these are called as also hydrogen halides. Also, they can called as haloacids also. Now I am coming to the acidic strength of the halogens increases. So HI is the very strong acid because in this HI, we can see here in this table, see the HI bond dissociation energy. See the HI bond dissociation energy here shown 295 kilojoule per mole. So it is having very less bond dissociation energy, means this bond can be easily broken. So the HI bond is very weak because iodine having the atomic size is very large. So this bond becomes very weak. So hydrogen can be easily removed. So HI is more acidic. This HI is acts as a strong reducing agent also because of these properties. And these properties of HF, you know the properties of HF, this bond is very strong bond. Hydrogen cannot be removed easily. So this is a weak acid and this is strong acid. This is thermally more stable. This is thermally less stable. And this is also the less reducing. This HF is having the less reducing properties, but this HI having the more reducing properties. This is strong reducing agent. This is weak reducing agent. So if you understand the bonding, we can write the acidity also, we can write the thermal stability also. All the points will be clear if you understand the bonding. And for the bonding, atomic and ionic size is very important. So as the HI is very strong acid, this is thermally less stable. So thermally stability we can see here. HF is more stable than HCl, then HBr, and HI is thermally less stable. But this is a strong acid and this is weak acid. So if the thermal stability is more, the acidity decreases here. See, the acidity decreases. This is acidity and the thermal stability is vice versa. These are opposite. Strong acid means thermally less stable, and this is a weak acid is thermally more stable. We can see the order is completely opposite. See, HI is a very strong acid, but the HI is thermally less stable here. So it is written in exactly opposite forms. This is acidity increases and stability decreases here. So HI is thermally less stable, but the HI is very strong acid, remember. And these are shown as the bond dissociation energy. HI is having very high bond dissociation energy because of the bond is very strong, and HI is having HF is having very strong bond, and this HF is very strong bond. HI is very weak bond. This is shown in this table also. See, the bond dissociative energy of HF is very high, and the HI is very less. And I'm coming to the noble gases, the group 18 elements, the noble gases. You know, these noble gases having the electronic configuration or the outermost outermost shells are already completed. They are chemically inert towards the hydrogen. They do not react with hydrogen, remember. So we discussed today the oxidation states of group 16, 17, 18 elements, then the reactivity with hydrogen. Then the next part is reactivity towards oxygen. So all these group 16 elements, 17 elements, and group 18 elements, we will discuss one by one. Reactivity towards oxygen, they form oxides. When they react with hydrogen, they form hydrides. When they react with oxygen, they form oxides. So we will discuss first group 16 elements. Group 16 elements is oxygen family. So this oxygen family reacts with oxygen. They form two types of oxides, remember. EO2, where E is element. So dioxides, and also they form trioxides, where E is equal to sulfur, then selenium, then tellurium, and then polonium. These are the elements of the oxygen family. Old style say TPO, remember. This is a short form to remember. Old style say TPO, old for oxygen, style sulfur, say selenium, T tellurium, and polonium. So first we will discuss these CO2 types of oxides. This ozone, sulfur dioxide, these are the gases, while this selenium dioxide is a solid. They are acidic in nature. They react with water to form acid. So we'll discuss these reactions when sulfur dioxide. Sulfur dioxide, it is EO2 type of oxide. This reacts with this H2O to form sulfurous acid, H2SO3. And this selenium dioxide reacts with water to form H2SeO3. This is selenious acid. The reducing property of the dioxide decreases from SO2 to TeO2. SO2 is more reducing, while TO2 serves as an oxidizing agent. Then I am coming to the EO3 types of oxides. SO3 sulfur trioxide, selenium trioxide, and tellurium trioxide. These are also acidic in nature. They dissolve in water to form acid. So these EO2 and EO3, these are the same reactions. The sulfur dioxide also reacts with water to form acid. This selenium trioxide reacts with water to form the selenic acid. Here, selenious acid for SeO2, and for SeO3, this is selenic acid, H2SeO4. So these are the types of oxides. This is EO2 types of oxide, and this is EO3 types of oxide. And this is a TeO3, that is a tellurium trioxide, reacts with 3 molecules of water. They form telluric acid. So for 1 mark, these reactions can be asked, remember. For 1 mark question, these reactions can be asked, and how the question is asked, what is the reaction of SO2 with water? So the reaction of SO2 with water, they form the H2SO3, not H2SO4. H2SO4 is sulfuric acid, but 1 oxygen is less. It is called a sulfurous acid. And this is a selenious acid. So remember, on this point, on this part, 1 mark question will be asked on this reaction. So we have to make a practice of these reactions. What is the reaction of SO2 with water? What is the reaction of SeO2? That is selenium dioxide with water. And this is oxygen with selenium trioxide with water. And this is a tellurium trioxide with water. So today we have to make a practice of these reactions and write the products, and also paste this chart, whatever the chart we prepared in your study room, because this is not very easy to remember. By making practice, we can remember these reactions. These are not very difficult. These are very simple reactions, not organic reactions. These are all inorganic reactions. Then I'm coming to the group 17. This is very important, because many times group 17 elements, the question is asked. No any question is asked on this part yet to the board exam, reactivity towards oxygen. But for 1 mark, they can ask the question, remember, for these reactions and for this reaction, EO2 types of oxides and EO3 types of oxides. But this on this part, oxides of group 17 elements, many times, I think from for 10 to 20 times, the question is asked for the board exam on this part. Oxides of group 17 elements, that is oxides of halogens. Group 17 elements are the fluorine, chlorine, bromine, iodine. They react with oxygen to form oxides, but many oxides are unstable in this. These fluorine oxides, you know, the oxides of OF2, this is already discussed in the previous part also. OF2, there are 2 oxides of fluorine, OF2 and O2F2. Only the OF2 is thermally stable. So this OF2 is the only oxide of fluorine which is having oxygen is having +2 oxidation state, remember. And in case of this O2F2, this is not thermally stable. This is thermally stable at 298 degrees Celsius. Both are the strong fluorinating agents. This is the use of this O2F2 is given. O2F2 oxidize plutonium to form PuF6. So this is important for the examination. What is the role? What is the use of this O2F2? So O2F2 oxidizes plutonium to plutonium hexafluoride and this action is used to removing the plutonium as plutonium F6 from the nuclear fuel, the spent nuclear fuel. Then I'm coming to the oxides of chlorine. Chlorine forms these oxides Cl2O, ClO2, Cl2O6, Cl2O7. These are highly reactive and oxidizing agent. This is ClO2. This is used as a bleaching agent for paper, pulp, textile industries, also in water treatments. This ClO2, remember this ClO2. So the bromine oxides are Br2O, BrO2, then BrO3. These are also the least stable. As I discussed earlier, most of the oxides are unstable. So the chlorine 2 oxides, then 1, 2, 3, 4, chlorine 4 oxides, bromine 3 oxides. So remember the name of these oxides. Also, we have to prepare one chart of these oxides. Oxides of fluorine, oxides of chlorine, oxides of bromine. So practice is required. By making practice, we can remember these oxides. Because for 1 mark, the question will be asked on what are the oxides of chlorine, what are the oxides of, which are the stable oxides of fluorine. Such type of questions will be asked for the examination. Then I'm coming to the oxides of bromine. Br2O, BrO2, BrO3, these are the least stable oxides. We are in chemistry, these oxides we are not using very much because these are unstable. Then I am coming to the iodine oxides. Iodine form 3 types of oxides. First one is I2O4, I2O5, I2O7. These are insoluble solids, decompose on heating. In these, out of these I2O4, I2O5, and then I2O7, one this I2O5, this is very good oxidizing agent and used for the estimation of carbon monoxide. So such type of questions are asked. What is the use of I2O5? So I2O5, it is used to estimation of carbon monoxide. Then the higher oxides of halogens are more stable than the lower ones. And group 18 elements, as you know, the group 18 elements, they having the completely filled, s orbital is completely filled, the p orbital is also completely filled. These are chemically inert, they do not directly react with oxygen. Then I am coming to the reactivity towards halogens. Halogens are fluorine, chlorine, bromine, iodine. So group 16 elements reacts with halogens. They form EX6, where E stands for the sulfur, selenium, and tellurium. Means they form the large number of halides, hexahalides, tetrahalides, and dihalides. 3 types of halides they form when these reacts with halogens. First, we will discuss these hexahalides. Hexahalides means 6 halides are there. So this is sulfur hexafluoride. This is a selenium hexafluoride. This is a tellurium hexafluoride. Tomorrow we will discuss this reactivity towards halogens. So I request please go through whatever the part we discussed today, that is the chemical reactivity, oxidation states, then reactivity towards hydrogen, which is strong acid, which is weak acid, thermally which is more stable, oxidation state of oxygen family, oxidation state of the halogen family. So I'm going to stop here.